Hello, this is Monica Colpi speaking. My talk will focus on the detection of flashes of X-ray light as companion signals of LISA massive black hole coalescences occurring in gas-rich collisions. In essence, the question is, how can LISA and the X-ray observatory Athena work together to detect gravity and light together? The science cases of Lisa and Athena are individually outstanding and complementary. They both are exploring the violent universe. But the additional science from concurrent observations may provide unexpected breakthrough in areas beyond those each individual mission can achieve. In the domain of physics and cosmology, detecting the counterpart of a massive black hole coalescence will let us measure the speed of gravity and the Hubble expansion parameter out to cosmological distances. In the astrophysics domain, we will have the first and unique opportunity to learn about accretion flows in violently changing spacetimes where gravity is extreme and in emerging horizons associated to the newly forming black hole. We know about the environment, whether the coalescence was consumed in a hot, turbulent gas cloud or in a cooler circumbinary disk. LISA will provide of a black hole coalescence the amplitude, frequency and phase of the gravitational wave tracked on the fly, that is during the inspiral, merger and ring down, to let us infer the black hole masses individually, the spin moduli, and possibly also their projection or direction relative to the orbital plane, to let us evaluate the extent of the gravitational recoil early during the merger. It also will provide the luminosity distance and sky position, the two key parameters that will let us identify an X-ray source with Athena in order to infer the light curve, its periodicities imprinted that could be a clear signature of a coalescence event, and the spectra. The multi-messenger view I am proposing is really outstanding because for the first time we can cross-correlate two independent sets of data to learn about the environment of a merger and of the black holes themselves. But let me remind you that no transient AGN-like emission has ever been observed that could be attributed to a LISA coalescence event consumed over a timescale of weeks, days, but sometimes only hours. In the X-ray sky, very little is known about low mass, low luminosity accreting supermassive black holes inhabiting low mass dwarf galaxies. Thus, the feasibility of a multi-messenger survey relies only on theoretical modeling and on simulating observational strategies. Perhaps in the near future, machine learning algorithms for multi-messenger astronomy with LSST and Euclid might detect the light from a LISA coalescence to provide the first real template. Here is the outline of what remains of my talk. I will survey briefly a few models of circumbinary disk only around binary massive black holes. Then I will summarize some key findings on the LISA sky localization capabilities studied by Alberto Mangiagli and collaborators. I will then mention the strategy that the Athena team is planning to carry on in order to identify the X-ray source and also the host galaxy. And then I will try to tell how many of these coincident mergers could be observed during the lifetime of Lisa and Athena. So imagine two black holes surrounded by a circumbinary gaseous disk at the time of entrance in the LISA bandwidth. The LISA is recording the chirp and the X-ray luminosity coming from the disk in the post-decoupling phase, that is, when the viscous time is longer than the gravitational wave-driven timescale. In this post-decoupling phase, we might detect some X-ray periodicity that goes in tandem with the chirp. We don't know whether the X-ray luminosity will continue to stay constant or rise or decline, and also we further expect additional periodicities and features related to the complexity of the fluid patterns close to merger. Then we would like to know, after merger, when disk rebrightening will occur. After a few hours, days, weeks, or months? Could we also infer whether an incipient jet was launched by the newly formed spinning black hole? 2D post-Newtonian 3D GRMHD simulation of black hole binaries in circumbinary disks share universal features. The binary is excavating a cavity due to its quadrupolar torque. But contrary to previous studies, the cavity contains considerable amount of gas, as the circumbinary wall is leaky. Low angular momentum gas feeds constantly two mini-disks with two streams impacting on them and creating shocks. High angular momentum gas impacts on the inner rim of the circumbinary disk, creating a lump that is a nonlinear m=1 asymmetry in the density. Thus, it is clear that these variabilities, commensurate with the asymmetric fluid patterns, could give rise to variabilities in the light, optical, and in X-rays. And one example is the bit frequency between the lump mean orbital frequency and the orbital frequency of the binary black holes. In addition, erosion of the mini-disk due to tidal truncation and fast orbital decay may lead to a declining luminosity when the binary nears merger. Here I'm showing two examples. On the left, I'm showing the light curve by Tang et al. As a function of time, 20 hours before coalescence. You see a modulation, and superposed to this long-term modulation, there are higher frequency periodicities that could so be in relation with the observed chirp. The spectrum is broadband, is extending from the visible to the very, very hard X-rays, and the contribution to the X-ray flux, say between 0.5 and 10 keV, is coming from the mini disk and the hot shot cavity. On the left, I'm showing the new spectra calculated by Dascoli et al. In post-processing on the GR simulation by Bowen. Again, the spectrum is broadband and the contribution to the X-ray flux is coming from the mini disks. But this is theory. We know from the observation of active galactic nuclei that the X-ray emission from single black holes comes from UV and optical photons that are comptonized by hot relativistic electrons that are located within a so-called corona, which is very near the horizon of the black hole. And with some fantasy here, I sketched what could be the case of a binary system. So imagine that above the mini disk there will be or form a mini corona. The two black holes are moving with a relativistic speed relative to the center of mass, so an electromagnetic X-ray chirp, due to relativistic Doppler modulation in tandem with the gravitational wave chirp, could be detected, as has been suggested by Zoltan Hyman. In this way, we could infer the relative difference between the speed of propagation of gravity compared to light to a precision of 10 to the minus 17. But also imagine that now coalescence has occurred and we have a single black hole. Would a corona reform after merger so we could detect the X-ray light? This is what the Athena-LISA synergy will discover. Concerning the post-merger dynamics and associated X-ray spectra and luminosity, little is known. We know that mass loss due to gravitational waves makes the disk suddenly eccentric, and the fluid patterns are such that the fluid will try to recircularize. But kicks have major impact on the process of disk rebrightening, which in general is delayed. In short, deformed disks are source of energy dissipation, thus photon emission, and also there is unbound material, so disks are truncated. In this figure, I'm showing the beautiful hydrodynamical simulation of black holes and disk that received a kick. In the upper panel, I'm showing the shape of a disk associated to a perpendicular kick resulting from in-plane spins. The newly formed recoiling black hole is dragging part of the disk, and you can also see the unbound material forming a tenuous tail. In the case of an in-plane kick, due to spins parallel to the orbital angular momentum vector, and this is a quite likely situation in a gas-rich environment because we expect high spin for the black holes aligned with the vector with the orbital angular momentum vector. Here the black hole is piercing deep into the circumbinary disk, is creating a wake, and material is bound. The bolometric luminosity of these perturbed disks by recoiling black holes is shown as a function of time, as a function also of the mass and the kick velocity. The larger the kick velocity is, the higher is the luminosity, because the disks are more heavily perturbed. For a perpendicular kick, you see this rising luminosity at 0.1 year after merger. It is rising and then decline when matter is consumed. But for nearly in-plane kicks, the disk is tilted and matter takes a while to reach the innermost stable circular orbit, and the brightening occurs after a year following coalescence. Concerning the observing strategy on the fly, that is, as a function of the time to coalescence, we need to address two key questions. How well can we determine the parameter of the gravitational wave source, and how well can we localize the source with LISA to inform Athena? Athena carries on board a wide field imager with a field of view of 0.2 degrees, and it is sensitive to photon energies between 0.2 and 15 keV. It has a fast response time of 4 hours to observe any target of opportunity in a random field of the sky. That is, we need 4 hours for Athena to reach and cover the area that has been spotted by LISA. And just to give you the sizes of this field, I'm showing here the Chandral wide field image of the Bootes constellations covering 10 square degrees. This area is compared with the area covered by the wide field instrument on board Athena. But let me remind you that Athena can really be assisted by the Large Synoptic Survey Telescope LSST, which has a field of view of 10 square degrees. We carried on a parameter estimation during the inspiral only, as a function of time to coalescence, for 3 selected binaries of 3 times 10 to the 5, 3 times 10 to the 6, and 10 to the 7 solar masses located at redshift 1. We randomize all parameters of these sources from the mass ratio, spin, time to coalescence, and all angles. And here I'm showing the median of the signal to noise ratio as a function of the time to merger. You see that the sources can be detected 1 month, say a week, and a few days prior coalescence for the case of the light, intermediate, and heavy binary, respectively. These sources are extremely loud because at the end of the spiral, their SNR is above a few hundred, and at merger that we do not simulated, but we adopted, but we rescaled it using a phenom C waveform, you can see that at merger the SNR is in the thousands. Concerning LISA localization uncertainties computed using an inspiral waveform which also contains higher order harmonics, Here I'm showing in the bottom panel the delta omega. The medium shows that for these sources, for the light and intermediate binary, 10 hours and a few hours before merger, these sources will be in the LSST field of view, but instead Athena will be able to slew and detect the source when the merger is occurring. So when there is the peak of the gravitational wave amplitude. Please notice how broad is the uncertainties around the mean, since also we covered the full parameter space, so we might have better located sources that would facilitate their identification earlier, but we might be blind in sources that have a bad location. Concerning the chirp mass is pretty well measured when the sources are entering the LSST field of view with accuracy which are around 1%. Similarly, the mass ratio uncertainty falls below, say, 1% for all the sources concerning the mean, so we can learn and have an indication of the individual redshifted masses of the binary. The luminosity distance can be determined with an accuracy of 1% or less at merger if we neglect lensing. Concerning the Athena strategy and its average flux sensitivity indicated here for a 10 kilosecond of exposure time, Athena can stare at the source at merger and after merger to detect the rebrightening of the disk. If we consider a vanilla emission model, that is a source Eddington limit with a bolometric correction in the X-rays of 3%, unobscured AGN hosting the newly formed black hole of 10 to the 6 and 10 to the 7 solar masses can be detected at such flux level in 5 or 10 kiloseconds or even less, so in a quite short time scale. But if the new AGN is living in an obscured environment, so we are losing the soft photons, only the 10 to the 7 solar mass newly formed black hole has a flux that could be detected with 5 or 10 kilosecond exposure time, depending on the redshift. While for lighter black hole, it will be really troublesome because they could reach the confusion limit of Athena. In summary, we can study and localize which are the overlapping horizons of Lisa and Athena, considering their sensitivities and average limiting fluxes at full signal. This is a figure from McGee, Cesana, and Vecchio. You see the plane of the redshift versus the total mass of the binary in the source frame. The green triangle labeled 0.4 square degrees is telling us that all sources below such triangle can be detected by Athena at merger, so they are in the Athena field of view, but quite crudely, I also sketched the area that is common for Lisa and Athena. The blue triangle is indicating the loci where we can both see the source in light and gravitational waves if there is an unobscured active galactic nucleus, whereas the orange triangle is indicated the area for obscured active galactic nuclei. But is there the hope to detect the X-ray light during the inspiral phase, so rich of information concerning the fluid behavior in an extreme spacetime? This is indeed a very delicate interplay between a loud source and a X-ray dim source, because this detection is made possible if the binary is quite light. 3 times 10 to the 5 solar masses is our example. The source is entering the LSST field of view 1 month before coalescence, and 10 hours before coalescence, 10 hours before coalescence, the source will be within the Athena field of view with a flux which is pretty large compared to the limiting average sensitivity. The source cover during the LSST, when is in the LSST field of view, very many cycles, so there is really the hope to see the optical modulation associated to the orbital motion, and when within the Athena field of view we expect to see very many cycles, and so we might also sort of see the electromagnetic X-ray chirp. The strategy is the following. Athena is planning to cover the LSST area with tiles of equal exposure time until merging. It will cover the LSST field of view with 23 observations of 9 kiloseconds each, and tiles are centered to the best fit Lisa position, which we hope it will be updated on the fly. Here is just a sketch of the raster scan. The probability of the source to fall within the WFI of Athena, computed by Guainazzi during the spiral, is 80% for this platinum binary, but it falls below 50% for a million sun binary, and when the sources are at redshift larger than 1, the probability is dropping below 40%. Once Lisa localization is comparable to the Athena field of view, clearly Athena can stare to the predicted error box up to the time of merger. Concerning rates of common Athena and Lisa events, these are uncertain. Alberto Cesana has given an indication that we might detect 10 coincident detections, 10 counterparts over 10 years of operation for sources out of redshift 3. This little table has been computed by Ayird and by the Athena team, showing that we might have several optical and X-ray counterparts out of redshift 2 for these black hole masses. The bottom panel shows a beautiful picture coming from a very deep cosmological, high-resolution cosmological simulation by Volonteri et al. I'm showing the UGR images of ELISA merger associated to uh, merging dwarf galaxies. If we are going to detect low luminosity and low redshift counterpart to LISA events, the galaxy which is hosting may not show signatures of a merger because there is a large mismatch between the time the two low mass galaxies are merging and the time the two black holes inspiral and reach coalescence. Here is my summary. Athena is optimal to identify post-merger signatures of black hole coalescences out of redshift 3 for the masses indicated here. Athena can explore the merger field post facto and continue to monitor the field with suitable cadence in order to witness the rebrightening of the disk or the surroundings of an incipient jet. We are dealing with very, very loud gravitational wave sources, and those with arc-minute localization uncertainties could also be observed with the X-ray integral field unit to do spectroscopy. Athena can detect the inspiral of very light, a few times 10 to the 5 solar mass nearby binaries in synergy with LSST. Fields are crowded of galaxies, and exploiting the information of the luminosity distance from the gravitational wave signal may help reducing the sky volume to identify the host galaxy and do cosmology and fundamental physics. Thanks for your attention.